Hello, this is Professor Elliott again, and in today's video lesson we will be exploring the basics of the op-amp or operational amplifier, as it's properly known. So for the course, we'll be looking primarily at the 741 series. There's other types. This is sort of a medium performance device. It's very popular. It's been around for decades, and it's a really good one for you to get to know. Okay, so first of all, the op-amp is available in some different package styles, and just gonna turn on my pen and the color. Let's go for red. So this tile here, this is called a DIP, or dual inline pin, and obviously that'll fit right in your breadboard, but it's really designed to be go through a through-hole circuit board and then be soldered on the back side. These pins. This is surface mount, and it's also meant to go on a circuit board, but it's going to be soldered just on the one side. So these next few slides are just cut and paste various bits from the data sheet, which you can easily find online, just to highlight some of the more important points. So we have the device pinout. Notice that it's a 8-pin device, and you can see all the powers and the grounds and the inputs and things like that. And it is NC means not connected. It just means it's a non-functional pin. It's just there on the package, but there's nothing there, so you just don't do anything with it. And here's a bit of a poor photograph of what it looks like. Internal schematic, if in case you're interested. There you go. And so basically what you have here is you have a different input differential amplifier. So the op-amps will work down to AC or DC, and they're not capacitily coupled, so they can work down to DC. And so that's sort of the input stage. The output is we'll call a push-pull output stage by this NPN and PNP transistor. So it's a differential signal in, then it's a single-ended line out. The power supply is plus VCC. They have minus VEE. They can run single-ended, or it can run the single power supply or the dual power supply. So it's quite versatile, and just depends on the application. So anyway, okay, partial data sheet. Okay, I know this is really exciting, and there's lots of stuff here, but there's some of the main things for you to consider. And depending on the suffix, and this is something you'll have to get to learn if you start working with data sheets, okay, is that sometimes there can be slight variances in the part numbers, slightly different characteristics, and they'll change the suffix to denote that. So anyway, you can see that they have the power supply, okay, it's maximum plus or minus 22 for all of them, but if it's a 7041C, it's only plus or minus 18. Okay, power dissipation, differential input voltage, okay, 30 volts, and input voltage is plus or minus 15 volts. Gives you the temperature range here. Again, this isn't everything, it's just sort of cut and paste some of the more things you might find of interest. Okay, so here's a little bit more. Okay, so we have things which we'll be talking about through the course: input offset voltage, average input offset drift, input bias current, input resistance. Right? Notice that the input resistance typically is 6 megohms. This is very high, so it doesn't draw very much current. This input offset current is sees down to 3 nanoamps. Okay, so that can be well, we'll explain that later in the course what that is, but better not to do it now. But you can see the currents down in the nanoampere range. It's very small. Look at the look how much ohms we have here. Okay, and notice that we have minimum values, we have typical values, we have maximum values, And so obviously here, if the maximum is 3, they give you a typical. Obviously, the minimum is going to be 0. So they don't actually tell you everything, and because you're supposed to know what you're doing if you're actually reading the data sheet. So they just sort of give you the minimum information that you need to use and work with the device. Okay, so just some more key parameters. You can have a look through those, and we'll be going through these again as we poke along through the course. Okay, op-amp input modes, and so we're going to take a look at those. Okay, so this is fairly important. So we have single-ended, and just some typical examples here, where we have just a battery. Okay, obviously that's the plus side. Note that's going to the negative, or it's called the inverting input. Sorry, this is the positive. This is the non-inverting input. Inverting, non-inverting. There we go. Sorry, it's early in the morning. Okay, and anyway, but only one signal is applied. So the other input is tied to the ground of the common. The input goes into the one side. The differential voltage is simply the difference in potential between these 2 points. And if this was, just for example, 1 volt, then the differential voltage would be 1. Okay, over here, again, we have a battery, and this time we're going into the non-inverting input there, and the inverting input is tied to ground. Okay, so I'll explain more what the difference between using these two input means later, but that's single-ended, and all that means is one of the inputs, either the inverting or non-inverting input, is referenced to the ground. Okay, and that's how you know you have a single-ended input. Double-ended differential. So again, some examples here. We have batteries, and source doesn't have to be batteries by any stretch. That's going to be a positive. That's going to be a minus. So we're using both of the inputs here. So it's double-ended differential. Double-ended, it's always differential because the inputs are always taken from the input potential between these 2 points. It's double-ended because we're using 2 input voltage sources rather than just the one, as you looked at on the earlier slide. So okay, so over here we have a positive, right? Positive, so they're both the same polarity. Over here it's a positive and negative, they're different polarity. Here we have an AC input, and this, notice that this AC input, there's no grounded reference. It's like a floating common. And of course, this point here is going to be look something like this, and this is going to be like this. So it's differential because it's really hard to draw with the mouse, 180 degrees phase shift. Okay, so please take the time to read all the important notes and before moving on to the next slide. Okay, all right. Okay, common mode. Common mode is when we're applying the same input voltage goes to both sources. Okay, and if these two were exactly the same voltage, then it'd be common mode. Examples of common mode are noise, and we'll be looking more at that in the instrumentation amplifier a little bit later. So common mode, the input signals are applied to both op-amp inputs, and they have to have the same amplitude voltage and exactly the same phase and frequency. So it's the same signal. All right. So again, all the important notes for you I've left for you there. Okay, so please read them. Okay, CMMR is known as sounds big and fancy, but it's really quite simple, common mode rejection ratio. And so there's 2 modes. So first of all, there's open loop. Open loop, there's no feedback resistors, which basically means that the smallest bit of differential voltage here will drive the op-amp transistors. Remember we talked before about the push-pull output transistors into saturation. And so common mode is a ratio, and it can be expressed as as sorry about that, as a ratio here, or as a dB. Okay, and the formula is the common mode rejection ratio is the open loop gain divided by the common mode gain. Again, A, don't know why it just is. A is equal to voltage gain. Okay, I'll be doing some follow-up calculations in class. This is just so you kind of know what we're talking about when you come to class. But the open loop gain is not very well controlled. It's kind of similar, not the same thing, but like beta with transistors is not well controlled. Well, this is not well controlled at all. Okay, and so that's why if you want predictable gain, you need to use feedback resistors, which we'll be going over quite thoroughly. But anyway, to give you a little example there, and we'll fill in any missing bits in class. And again, common mode, same signal, voltage, amplitude, and phase is applied to both inputs. Okay, so have a look through this, familiarize yourself with it, and we will do some examples in class and get everything straightened out. Okay, all right, thank you. Okay, so just on the data sheet, some typical values. Common mode rejection ratio, okay, has a typical value of 90. These are all in dBs. Okay, so it gives you sort of a typical value to rule of thumb value to work with, and that's it for that. Okay, slew rate is basically the rate of change of the output. So if you needed higher performance or the output to switch at a faster rate, then you'd probably want to use a different op-amp than the 741. But anyway, so it's sort of a medium performance level. Okay, so you're going to be doing a lab on this, so I'm not going to spend a ton of time here. Not sure why it's jumping like that, sorry. But anyway, you provide a step input. Look at here to the non-inverting input monitor with the output. So this line here, the orangey tan colored brown one, is the input, and this is the triangle wave is the output. And when the output transitions from the 90% point to the 10% point, then that's the slew rate, and you can see the calculations there. So the better, the higher performance the op-amp, the less the time it takes to transit from this point here, 10% point to the 90% point. So it's said to be faster switching. Again, the datasheet gives you a typical value. Okay, and for 741, it's a typical value of 0.5 volts per microsecond. Okay. Okay, input output impedances. There's a lot of just miscellaneous stuff in this slide in this presentation that you need to know. So ideally for an op-amp, the input impedance, which you recall from last term, ideally is going to be infinite, and the output impedance is going to be 0. So this is the ideal. All right. For the non-inverting amplifier, okay, notice we have here. Okay, we have feedback resistors here. Notice that the input impedance is actually modified by the feedback. So one thing that feedback resistors do is that it allows you to provide predictable, stable gain by selecting the right value of resistors. And it also makes the both the input and output impedances much more ideal. Okay, so it actually makes things better. So this gives you some typical terms. So the input impedance open loop, okay, you can pull a typical value from the data sheet. Output impedance open loop, again, pull a typical value from the data sheet. Input impedance closed loop, output impedance closed loop. We know it's closed loop because we have these resistors. Okay, so it's a closed loop amplifier. That's normally what we're going to have. Okay, so that's the closed loop input impedance. Okay, if you're interested in the formulas, and they're down here, so don't worry, we're going to cover it in class. So, but again, the input impedances are increased. Okay, output impedances are decreased. So by having feedback, it makes these right, work out to more the ideal of infinite here and 0 there. Okay, again, more stuff, more to follow in class. Inverting amplifier, same idea. The equations are just a little bit different. This is going to take a little bit of time to explain. So, but anyway, just sort of familiarize yourself with it the best you can, and we will cover it thoroughly in class, I promise. Okay, voltage follower. Voltage follower is used as a buffer or an isolation between two different points in the circuit or stages, where particularly where there's an impedance mismatch. The input impedance of the voltage follower is very high, very high, and the output is very low. And you know you have a voltage follower when you see this tie back to the inverting input, and there's no resistors. Okay, so again, that will be covered quite well in class. Well, so that's the end. Lots to go through. I hope you enjoyed it. Please feel free to go back and review things as much as necessary. But we'll be covering it, picking up from this in class, and working through examples and filling in all the missing bits. So you should be all good to go. All right, catch you soon. Bye bye.